Hi everyone, this is teacher Benard from Trinity College Nabingo, and today we are looking at azeotropic mixtures. This is a continuation of physical equilibrium for miscible liquids. We have been talking about azeotropic mixtures, and we have been seeing that solutions that deviate negatively from Raoult's law, that is, those ones that form negative deviation and those that form positive deviation, they always form azeotropic mixtures at certain compositions. So now we want to go into the depth of azeotropic mixtures. What are azeotropic mixtures? If we consider the boiling point composition diagram below for solution between liquid P and liquid Q, we are assuming liquid P and liquid Q are miscible and that liquid P is less volatile. Liquid P is more volatile and therefore it has a low boiling point, and liquid Q is less volatile and therefore it has a high boiling point. If they form an azeotropic mixture at composition 60%, you will note that the azeotropic mixture will have the highest boiling point since it has the lowest vapor pressure. Now, what if we are told to describe what happens when a liquid mixture containing 60% Q is fractionally distilled? I want you to know that 60% of Q is where liquid P and liquid Q form the azeotropic mixture. And I want you again to note that at that point, the composition of the vapor and the composition of the liquid mixture, they intersect. So that means that if we heat the liquid mixture at that composition 60%, the vapor we get will have the same composition as the liquid mixture. That means that it will have also 60%. And then if we cool that vapor we get, we shall again get a liquid of the same composition, 60%. So that means that at this moment, when we have the azeotropic mixture, the composition of the liquid mixture and the composition of the vapor are always the same. And therefore, it means that the azeotropic mixture, since the azeotropic mixture has no tendency to eliminate one of the components, it may not be easy to separate using traditional fractional distillation. So you may be posed with a question, describe what would happen if a liquid mixture contains 60% used fraction and distilled. We have already seen that a liquid of composition 60% when heated, its temperature rises till it boils at a constant temperature Ta. So it will boil at a constant temperature Ta, giving an equilibrium vapor of the same composition as the liquid. When this vapor is cooled, it forms a liquid of the same composition as the vapor. That's how azeotropic mixtures behave. And because there is no tendency to eliminate one of the components, it means that we cannot separate them easily using traditional fractional distillation. A liquid mixture that behaves like this is what is referred to as the azeotropic mixture. So the azeotropic mixture is the one like when you heat it, it gives a vapor of the same composition as it gives us the vapor. It gives off a vapor of the same composition as the liquid. And we shall look at the definition. And since it boils at a constant temperature, it means that it is behaving as if it is a pure liquid. It is also referred to as the constant boiling point liquid mixture. So you'll find in some texts they are calling it the azeotropic mixture, or other people are referring it to as the constant boiling point liquid mixture. So if we look at this diagram, it means that Ta is the boiling point of the azeotropic mixture and 60% is the composition of the azeotropic mixture. Now, What are azeotropic mixtures? We are still looking at what they are. This boiling point and the composition of the azeotropic mixture will remain constant as long as the external pressure remains constant. What we are talking about here is that if you change the external pressure, the boiling point of the azeotropic mixture tends to change. And also, what happens if we change the external pressure? The composition of the azeotropic mixture will also change. So, those two things. However, that one distinguishes, it helps us to know that azeotropic mixtures are not compounds. Because for compounds, their boiling points may change with changes in pressure, but their composition will not change with changes in pressure. For example, water will remain H2O. It will always remain with 2 moles of hydrogen and 1 mole of oxygen, no matter the pressure. So the composition of the compounds don't change. But the composition of the azeotropic mixture changes with the changes in pressure. So that's what we are talking about here, that this boiling point and the composition of the azeotropic mixture will remain constant as long as the external pressure remains constant. So that is to say, that one means that the composition of the azeotropic mixture changes with changes in pressure. That is an important thing to note. It also means that the azeotropic mixtures are not compounds, because if they were compounds, their compositions would not change. Like water is a compound and its composition does not change. It will always remain H2O, whether the pressure changes to what. But for azeotropic mixtures, when the pressure changes, their compositions change. So, how can we then define azeotropic mixtures? From the above explanations, we can define azeotropic mixtures as liquid mixtures of 2 miscible liquids which at a constant pressure boil at a constant temperature to form a vapor of the same composition as the liquid. Did you get that? Liquid mixtures of 2 miscible liquids which at a constant pressure boil at a constant temperature to form a vapor of the same composition as the liquid. We have already explained that from the diagram. The composition of the vapor and the liquid mixture, for the azeotropic mixture, the compositions are the same. But you must put constant pressure, must be part of your definition, and then boiling at a constant temperature must also be part of your definition. And then giving off a vapor of the same composition as the liquid, you must also talk about that. So this means that azeotropic mixtures, since they give off a vapor of the same composition as the liquid, it's not easy to eliminate one of the components because the composition of the vapor is the same as that of the liquid mixture. That's what we are talking about here. This means that azeotropic mixtures cannot be separated by fractional distillation. And this is because the vapor formed on heating, the azeotropic mixture has the same composition as the liquid mixture. And hence there is no tendency to eliminate one of the components, like in other mixtures which are not azeotropic. So what are then the characteristics of azeotropic mixtures? From what we have been talking about ever since our lesson began, from the diagram, what we have been seeing, I think we can now get the characteristics ourselves. They have a constant composition at a constant pressure. As long as the pressure is constant, their composition will also be constant. They have a constant boiling point at a constant pressure. If the pressure is constant again, their boiling points will also be constant. And another thing we need to note is that they cannot easily be separated by traditional fraction distillation. And why is that so? Can you explain why we cannot easily separate them by fraction distillation? It's because when you heat the liquid, there is no tendency like the vapor formed is rich in the more volatile component. Because what helps us in fraction distillation is that successive heating and recooling of the vapor causes the more volatile component to become richer and richer in the vapor formed until when we get it as the distillate, and then the other less volatile component we get it as the residue. But now the azeotropic mixture, for it, since when we heat it we get a vapor of the same composition, it means that there is no tendency to eliminate one of the components from the vapor. You understand that? Because the vapor and the liquid are always of the same composition, so they cannot easily be separated by traditional fractional distillation. So then you can be asked to give differences between azeotropic mixtures and pure liquids or compounds. However much azeotropic mixtures boil at a constant temperature when the pressure is constant, just the way compounds behave, because like water, we know very well if the pressure is fixed at 1 atmosphere, it will boil at 100. So because it is a pure substance. But then the azeotropic mixtures, they are mixtures, but they are behaving as compounds also. You understand that? Like if the pressure is fixed constant, they will also have a constant boiling point, as if they are pure substances or as if they are compounds. So we need to look at the differences. Are they really compounds? Are they really similar? So there are some similarities and differences between azeotropic mixtures and compounds. And these differences between azeotropic mixtures and compounds tell us that truly they are not compounds. Because if they were compounds, they would not have these differences. So the differences are these. Azeotropic mixtures, their compositions change. Their compositions change with changes in pressure. That is one of the tests to show that azeotropic mixtures are not compounds. If their compositions change with changes in pressure, that means that they are not compounds, because for compounds, their compositions remain constant no matter the changes in what? In pressure. So the other difference between azeotropic mixtures and pure substances that again show us that azeotropic mixtures are not compounds or pure substances. In other words, that shows us that they are mixtures. The azeotropic mixtures can easily be separated using physical and chemical means. You know, in senior one we said mixtures can be separated using physical and chemical means, but compounds cannot easily be separated using physical and chemical means. Towards the end of this lesson, we are going to look at how we can separate azeotropic mixtures. But compounds cannot easily be separated by physical or chemical means. So that one is another way to tell us that azeotropic mixtures are not honestly compounds. They are not compounds, they are mixtures. Another difference that tells us that azeotropic mixtures are not compounds, they have more than one components or type of molecules. So if you check the azeotropic mixtures, doing some chemical tests, we shall find that the azeotropic mixture has different components. But a pure substance, for example water, it has only one type of molecules. That is the water molecules. But in the azeotropic mixture, for example, an azeotropic mixture of ethanol and water, you will find there ethanol molecules and you'll find there also water molecules. So those are the some of the differences. Those are some of the differences between azeotropic mixtures and compounds. But they also have some similarities. Azeotropic mixtures have some similarities with compounds or pure liquids. We have already seen they all have a constant composition at constant pressure. As long as the pressure has not changed, the composition of the azeotropic mixture will be the same, will not change. And someone may think it is a compound because compounds also, their compositions don't change. But for the azeotropic mixtures, their composition is conditional. The pressure must be constant. So at a constant pressure, they all have a constant composition. And again, at a constant pressure, they all have a constant boiling point. So those are some of the similarities between the azeotropic mixtures and pure compounds. How can we then separate azeotropic mixtures if they cannot be separated using fractional distillation? One of the methods we can use is distillation using the third component. We can add a third component to the azeotropic mixture. For example, for the azeotropic mixture of ethanol and water, we can add benzene as the third component. Would benzene mix with water? By the fact that we have ethanol there, an organic solvent, it will help benzene to mix with the azeotropic mixture. Because benzene is also an organic solvent, ethanol is also an organic solvent. And since we are having three components, we shall have a mixture which we call a ternary mixture. This ternary mixture is having three components: benzene, water, and ethanol. I want you to note that the composition will not be the same. So since the composition will change, it will no longer be the composition of the azeotropic mixture. And since the composition is not that of the azeotropic mixture, that means that we have already done away with the azeotropic mixture. And what we do is that we distill this ternary mixture of benzene, ethanol, and water. And then, depending on their differences in boiling points, we shall obtain them pure in fractions, one by one. So that's one of the methods we can do. Distillation using a third component. And that's what we are talking about here. Maybe we can read through these changes. For example, for the azeotropic mixture of ethanol and water, benzene is added. This changes the composition of the mixture to a new composition that is not azeotropic. Fractional distillation of this ternary mixture, that is a mixture that has three components, water, ethanol, and benzene, leads to obtaining of pure ethanol, benzene, and then pure water, but in fractions. Fractions means parts. We first get one, and then another one, and then another one, depending on their boiling points. We are most likely to first get ethanol, then benzene, and then water, hence separating the mixture. The next method we can use is absorption method. In this method, like absorption, like the word goes, we absorb one of the components of the azeotropic mixture. For example, the azeotropic mixture of water and ethanol can be passed through anhydrous calcium chloride. You know from senior one that anhydrous calcium chloride can absorb water. So we can pass this azeotropic mixture through anhydrous calcium chloride. Anhydrous calcium chloride will be absorbing water, and then as ethanol passes through, as ethanol goes through. So anhydrous calcium chloride absorbs all the water in the mixture, leaving ethanol to pass through. And the other method we can use is the chemical method. As the word goes, that means that this one involves a chemical reaction. So in this method, normally we need to get a chemical that will form a precipitate with one of the components of the mixture. And then that component, one of the components will be trapped in the precipitate, and then the other component cannot react with the chemical we have brought, so for it to remain as a liquid. And then we filter it off as the filtrate, and then this this chemical, this precipitate, we filter it off. So in this method, a chemical that can react with one of the components of the isotopic mixture to form a precipitate is added. The chemical reacts with one of the components, forming a precipitate, which is filtered off as residue, and the other component is obtained as filtrate. For example, for the isotopic mixture of water and ethanol, we can add calcium oxide. Calcium oxide reacts with water to form calcium hydroxide, which is pairing a soluble and therefore white precipitate. So, we filter off the calcium hydroxide as the residue, and then ethanol is collected as the filtrate. And then we can also use molecular sieves on a large scale in the industries. And molecular sieves, they are microscopic sieves that filter liquids according to their molecular sizes. For example, the isotopic mixture of water and ethanol, you will realize that the water molecules and ethanol molecules, they don't have the same sizes. And therefore, we can pass this isotopic mixture through these microscopic sieves. And then, since the water molecules are smaller in size than the ethanol molecules, the water molecules will be able to pass through, but the ethanol molecules will not be able to pass through. So that means that we shall be able to make the water molecules go through, but ethanol molecules not to go through, and then hence separating the isotopic mixture. And that one is normally done at a high pressure for the molecular sieves. Thanks for following. You have been good students. Thanks for following. I remain teacher Ssegujja Benard. That is my email. That's my WhatsApp number. So see you next time. Next time we are looking at steam distillation. So be alert. Keep following the videos. Shall be looking at steam distillation. That is immiscible liquids. Thank you. Stay safe. God bless you. Nice time.